have two speakers, and it's my pleasure to introduce the first speaker of today, Chen, from National Center for Theoretical Sciences, and he will talk about foliated MLD and LCT. Yan, please.
Thank you. Thanks for the introduction, and I would like to thank the organizers for the invitation. Okay, so if you have any question, please interrupt me. Okay, so today I want to talk the foliated MLD and LCT. So first I will give you some introduction on the foliations, and then I will give you some classification results on the low canonical foliation singularities on surfaces. And then we'll talk about what I mean ACC and for MLD and LCT. And everything in this talk will be over the complex numbers. Okay, let's get started. So the foliation, we mean, so we start from a normal variety, and the foliation of rank R is nothing but the rank R coherent subsheaf of the tangent sheaf Tx, such that it is saturated. This means that this quotient is torsion-free. And the second condition is this is need to close under the Lie bracket. So so that means this foliation, this subsheaf is integrable. And in other words, we could talk about something called leaves. Okay. And because we are in a normal variety, and now this is coherent subsheaf, we could define the divisor Kf associated with to the foliation. And in the following way, we take a dual and take a determinant, and this is and the corresponding, or which pick a veil divisor, and we call it a canonical veil divisor for the foliation. Okay, so okay, that's right. So now we want to define what is singular locus. So from the definition, we know our TF is just we associate like this way. Okay, we'll just write in this way. And if you take a dual, okay, let me write here. So if we take a dual, this is just omega x double dual, and we have the map to the TF dual. And if you tell a wedge R, then it gives you this wedge R, because the foliation is this TF is rank R, so wedge R is just a determinant, or you tell a double dual again. So this is just OKF. So we could get this morphism in this way, and the co-supports of this V will define as our singular locus for this foliation. Okay. Now I want to say how because we want to to study the foliation in terms of the Mino model program. That is, we want to talk about the transformation under the birational, at least under the birational map. So let's say it. So for a birational morphism F from Y to X, if we have a foliation downstairs, we want to define the foliation upstairs. So the way is just like this. So because we know it's birational, so we know there's a big open set inside each, and this is isomorphic. So for any foliation on F, let me write here. So we could restrict this foliation on U And because U and V are isomorphic, so it also give a foliation. Here, let me still write this guy like this way. So we could actually we could extend this sheaf as a coherent subsheaf of this tangent sheaf of Y. That means we could find the extension, and let's say G. And this is actually still a coherent sheaf inside the TY. This is some exercise, I think, in Harshon's book. And so the problem is if this definition is well defined, and the answer is yes. It's just from the saturatedness. So if let's say if we have a two such extension, so these are equal. So we consider map from G1 to TY and then go to here. So on an dense open subset, you know this is actually 0. So it's generically 0. So then, but so I mean the image. So the image will be a torsion, but we say this is torsion free. So that means the image of this composition map is 0. So it's 0. So that means it induces a map, this map. So vice versa. So we could show that they are actually isomorphic. Okay, so this is the way we how we do the pullback foliation. Now I want to give you some idea what's happen on the surfaces and introduce what's the reduced singularities on surfaces. So start from the smooth surface, and if given a P is a singularity, so around this point P, now because we are on surfaces, so this foliation or the interesting foliation will be rank 1. So this actually around this point is associated with a vector field. So we could write in this way. So first observation is that the singular P is a singularity of foliation implies that this is actually vanishes at this point P. And moreover, if we feel this vector field as a function from C2 to C2, so we could consider its differential, and it will give you a 2x2 matrix. And if you evaluate at P, then and consider its eigenvalues, let's say lambda 1 and lambda 2, and we consider its ratio. So if some lambda is not 0, so we could consider its ratio. And if its ratio is not positive rational, then we say this is a reduced singularities. Okay, so this is seems complicated, but anyway, we will see. I will give you an example. We will see why we want to exclude the positive rational. So we have the theorem by Seidenberg. So it says that given any foliating normal surface, so we could resolve the singularities by finite many blow-ups. So what we saw, we say resolve means that upstairs we only have reduced singularities. Okay. So let me say why it's not, the first remark is the side damper cannot make better. I mean, we could not say we could result to a smooth foliation singularity, or I mean, no singularity. We cannot do this. The reason is that if we blow up a smooth foliation point, actually we get a new foliation singularities with the eigenvalue lambda is -1. So actually, if you do the calculation, let's say, consider this locally this vector field. So the leaves is something like this one. So if you blow up this point, actually what you see is a exception divisor, and this line, you see this is L tilde, and other leaves will look like this way. So actually, this point is a singularities, and with lambda equal to -1. And if you actually write down everything explicitly, the vector field around these singularities could be expressed in this way. So this is actually give you the eigenvalue -1. Okay, so maybe let's see what happened when the eigenvalue is at least positive rational. So now let's see the positive is +1. So that means locally we could, or at least in the formal coordinates, we could write this vector field like this way. So if you study this vector field, you will see all the straight line passing through the origin is leaves. So that means it's something like this way. So all the straight lines are invariants. So if you do the blow up, then you know what we see is that we will separate all the. Let me change the color. So what we see is that this is an exception divisor, and all the straight line will be separated. So, but all these lines are invariant. So you see this E is actually non-invariant. Okay, this is non-invariant. And actually, okay, but what happened when we have this one? So if you do this right now, this way, so we have already seen you like this one. So passing through a region, there are two invariant curve, and other are just looks like this one. So if you blow up, you will see like this one. You separate these two lines, and all other lines will look like this one. So actually, let's see. So actually, all this and this you could check. These two Fourier singularity has eigenvalue -2. Okay. And this E is still invariant. So some difference between the positive rational eigenvalue and non-positive one is that for all the positive rational cases, there are infinitely many leaves passing through these singularities. So at some point, if you do blow up, we will actually separate all these leaves and get some non-invariant one. And for all non-positive rational, actually there are at most 2 invariant curve passing through these. Okay. So any questions so far? Okay, so now let's introduce this definition for the Fourier singularities in terms of the mini-model program. Let's say we want to talk about what is log canonical. So if we have a variety X and there's a proper birational map Y to F and a Fourier downstairs, for any exception divisor upstairs, we define this discrepancy. We say the Fourier discrepancy in the usual sense. So I mean, is defined to be the order of this big difference of divisor along this E. And we say this point is terminal canonical, log canonical if these numerical conditions satisfied. So here we have some difference. I mean, we need to take the invariance for the Fourier into consideration. So for log terminal and log canonical, here we involve the epsilon E here, and epsilon E is 0 when E is invariant, and is 1 is not invariant. Okay, so next, let me explain why we need this epsilon E. So let me recall the definition here. So this is a definition for the log canonical. So we notice that when the Fourier is of full rank, what I mean is that this F or TF is actually TX. So KF is KX. So actually this is reduced to the classical case. And in this case, it's not hard to see that all divisors are non-invariant. So non-invariant, so that means epsilon is always be 1. So we reduce to the usual definition for the log canonical. Okay, so here we only explain why epsilon E should be 1 for E is non-invariant. So how about for E is invariant? So another feature for the log canonical is that if the discrepancy less than this some number, then it will be negative infinity. So what I mean is that if you consider an invariant exception divisor, and let's assume it has a negative discrepancy, let's say negative C. So what we can show is that let me write it down. So you start from an E, and you can first choose a point, a general point. So actually we want a smooth Fourier point. So you do the blow up. Then what you see is something like this, and another exception divisor. But for the discrepancy, this one is negative C, and this Fourier singular for the Fourier discrepancy will actually be 1. And here actually introduce a Fourier singularity. This is important because if you blow up again, then let's see. So what we will have is something like this. So this is negative C, and this is 1 again. But for this green line, actually is 1 minus C, just the sum of them. Because this is a reduced correlation singularity, it itself, it won't give you any discrepancy. So all the discrepancies coming from these coefficients. So you see, so you just need, what you just need to do is you keep draw up this point, and you will get a discrepancy 1 minus NC for n is just some positive integers. So that means if you take the increment, there will be negative infinity. So we want to exclude this for our low canonical singularities. So that's the reason why we define the epsilon E to be 0. Okay, another reason is that we could have an adjunction formula in this way. So we could, no matter what E is invariant or not, we could have this delta, and this is actually effective. Okay, let me see. So, this adjunction may be actually not behave well in the foliation setting. I mean, if we know this is, I mean, even we know this is log canonical for the pair, this is not necessarily log canonical. So we will need to dealing with this later. Okay.
So how do you define FE in general?
Well, you just take a restriction on this guy. So let's see. We have TF. I think we just need to do the pullback, at least on the smooth locus. So you just, okay, let me just pretend everything is good. Okay, so you just take the pullback. So for if everything is good, that will give you something T. It's still the tangent shift.
Yeah, so do you look at E or the normalization of E instead?
Oh yeah, okay, yeah, that's a good point. Yes, that actually I take the normalization. Yeah, so that, yes. So let me write carefully. So this should be normalization. Yes.
Oh, thank you.
Yeah. Okay. Okay, so next so for the canonical singularity on the surfaces, there's some classification results by McQuillan. So he shows that if we have a canonical singularity on surfaces and we consider the minimal resolution for this point, I mean, and this minimal resolution is for the ambient space. And if you consider the exception device, let's write in E, then actually this E will belong to one of the following types. So actually, you will see something like this. So AM type, I mean, so it looks like the chain of the rational curve. And here I draw a red point, means that this is actually the reduced singularity for the foliation. Yeah, because we want to resolve the foliation. So I actually need to mark all the foliation singularities. And actually, and let me draw right here. So this is, and this blue line is invariant rational curve. And all the dotted, this is reduced singularities. So for the M type here, actually we have this like this one, or actually we could have one more singularities at the end, or there's some special case like this one. And for DN type, we have like this one. Oh, there's a one here. And here there's a elliptic Goranson leaves. So in this case, it looks like this one. And this is reduced singularities, and or just a cycle of the P1s. And these intersections are all reduced singularities. Okay. Okay, so this is for canonical singularities. So later I try to classify all the log canonical Fourier singularities on surfaces. So this is the statement. So now we start from the log canonical singularities.
So can you explain why the EN type is not possible?
Oh, you mean E type is not possible? Well, I think it's pretty hard to tell. It's let's say, let me think how to. It's like if you. Okay, I would like to say in this way. So if you consider E-type singularity, then its structure will give you will make this discrepancy less than 0, maybe for the Fourier singularity, Fourier discrepancy less than 0, and in this case it will be non-canonical.
But could it be log canonical?
Yes. Yes. So, but if we want to be log canonical, then the negative discrepancy, I mean, for the curve with negative discrepancy must be non-invariant.
Okay. Yeah, thank you.
Yeah. So, and thank you. And that's actually happen or appear for the log canonical singularities. So for log canonical singularities, actually, we do have the case that the exception divisor will be non-invariant. So, and actually all of them, I put it into a type called star shape. So that is, there will be only one exception divisor, which is non-invariant, and all are invariant, all others are invariant. And the length for all the chain of the P1s are unlimited. You could be as long as you want, and you could be as many as the chains you want. I mean, so if you tell a dual graph, this will looks like the center will be a non-invariant one, and all others will look like this one. So, and you could have more branches. Okay, let me draw one branches. Okay, like this one. So this will give you a star shape. And so for the E-type singularities actually happen here. So that means for the E-type surface singularity, if there's a foliation singularity on it, it at least be a low canonical, or in other words, it cannot support a canonical foliation singularity. Yes, any questions? So now let's move on to the minimal load discrepancy. So since we have already classified all the low canonical foliation singularities on surfaces, so we will interested in this property, ACC property. So let's define first the minimal load discrepancy. So you will define in this way. So for the classical one, this will be +1 here, but because we are in a foliation setting, so we plus this epsilon. So recall the epsilon is 0 for this E is invariant, and this is 1 is non-invariant. So we define this minimal load discrepancy. So the theorem says that if we first fix DCC sets, DCC sets means that any decreasing sequence will be permanent or eventually stay constant. So if we consider first fix a DCC set, then this set will satisfy ACC. So this set consists of all the minimal discrepancy and of the foliation on surfaces. And this boundary must have a coefficient belongs to this DCC set. Okay, so some example is that for B, when B is only 0, that means we don't have a boundary. So from the classification, we could show that the minimal load discrepancy is nothing but 1/n in this form. So you see this is actually a ACC set. Okay, so the proof, I won't show you the whole proof here, but I will just say something. So the proof actually follow the Alexis idea. So let me maybe say first, the difficulty for proving this is first, if we want to show this is ACC, so that means we want to consider first a sequence of these minimal load discrepancy. But the problem is that each minimal load discrepancy does not necessarily come from the same surfaces or the same foliation. Yeah, for most of the time, it will be different surfaces and different foliation. And those surfaces and foliation in general don't have the map between them. So this is the first difficulties. And the second one is for device computing this minimal load discrepancy is not necessarily on the minimal resolution. So for most of the time, we need to go to the higher model to find this divisor. So the proof is, the ideal proof is like this. So first we consider only the exception divisor on its minimal resolution. So here, that's what I mean. So if we only consider the exception divisor on the minimal resolution and take its minimum, and if you take the set consisting of all such minimal load discrepancy, we could show that it satisfies ACC. But this this number or this set does not necessary to be a minimal law discrepancy. So we need to do next to, we need to go higher. So we need to control, actually we just need some blow up to get to the some model which have a divisor computing minimal law discrepancy. And we could control how many times we need to do the blow up. So that's the second one. So we try to control the number of the number of blow up from the minimal resolution, and using this finiteness and also the ACC property on the minimal resolution to conclude that actually the minimal law discrepancy satisfy the ACC condition. That's the idea. So and maybe and all the proof is actually followed from the Alicev idea, and the some ingredients, first the classification of the singularity, and also we heavily use some linear algebra. What that means that the intersection matrix should be negative definite. Okay, any questions? Now, another interesting or another important invariant is low canonical thresholds. So this is defined in the following way. So we consider two DCC sets. One is inside 0, 1. One is just in the positive real numbers. And if we consider a validity variety and also another divisor n, and this, and we fix we control the coefficient. That is the coefficient for the boundary is inside this I, and the extra divisor, this m, is the coefficient is inside J. So the low canonical threshold for this pair respective to m is defined in this way. Okay, so when foliation or f is just the whole Tx, this is just the same reduced to the same definition for the low canonical thresholds. And we have to know that the set of low canonical thresholds satisfy the ACC by Hecken-McKernan and Xu. Also, this is interesting because we know ACC for MLD could imply ACC for LCT, and this is by Bill Carr. Okay, and now later I will only focus on one. So for the one, the proof is actually by adjunction. We try to use adjunction, and then we could reduce our dimension. So we tailor using some inductive argument on dimension. So actually, this is a rough idea how they prove the low canonical threshold satisfy ACC, and we will adopt this idea. Okay, so here's a statement. So
excuse me, I think there's a question from chat.
Oh, sorry.
So the question is, how do you define the foliated pair? Is the boundary divisor foliated invariant?
Well, that's a good question. Well, at first, when we define a foliated pair, we didn't restrict ourselves. We didn't put any constraint on the boundary divisor. Well, it need to be effective in general, but we allow it to be invariant. But it turns out that if we want to consider a low canonical pair, then by some similar argument I present before, if the boundary divisor is invariant, then it will not be low canonical. So in other words, if we want to impose the pair to be low canonical, then all the boundary divisor will be non-invariant. Okay. Okay, so any other questions? Okay, so now here we also fix two DCC set, we say I and J, and then now we only focus on the surface or threefold. That means I only consider dimension at mode 3. Then this set also satisfy ACC. So some ingredients to prove this is first we will use the so-called 480 MMP developed by the Paulo Cassini and Karen Spicer, and to get a so-called DLT modification for this pair. So, and then we could take a junction and Taylor junctions, and then the difficulty, I think the main difficulty is that we will try to control the singularity after a junction. So again, the problem is that even this is a low canonical pair, it won't, or it's not necessary. This is not necessary to be low canonical. Okay. So let me give you some idea how to prove in the case of surfaces. So if we first fix a DCC state, and okay, let's put an F delta be a 480 pair on the surface, and this is belong to I. And if this P is a local center for this, that is if you take some resolution, there's a exception divisor over this P such that the discrepancy or low discrepancy is 0. And the interesting thing, I mean, we will also impose P should be inside this, in the support of this delta. Otherwise, we could just ignore this boundary. So first, we have a DLT modification. Yeah, you could find this modification from the 480 MMP, or you could use the classification. But anyway, you could show that this DLT modification, I mean, we could have this DLT modification such that the exception divisor over this point have the property in this way. So it will be a chain of P1s, and these are reduced singularities. Yeah, actually we not necessarily go to, we are not go to the minimal model, so we have some singularities, I mean surface singularity. So we could show that the surface singularity must lie on the first curve. That's right here, and only one. Okay, so let me point out this is, let's say this is the first curve, E1. Okay, so so after we have this DLT modification, And this is not hard to show that this existence of this finite subset. So let's see. So the proof goes in this way. So we just tell the intersection number. So this is just a pullback. So we see here, this is just a pullback. So if you intersect with E1, this should be 0. And by some computation, it's not directly computation, but you need to go to a minimal resolution and to resolve this singularity to see what's the intersection number for this. But if you do this, this intersection will give you -1/m, where this m is the index of this singularity. And all other, I mean, for the delta y intersect with E1, because the index is m, so we could write this in this way. So let me say, let's write dy is just sum of j dj, like this one. And this kj will just positive integers. Okay, so it gives us so let's put here. So it gives us the summation j k j dj is equal to 1. So now if you remove, I mean, now remove, we just move j equal to from 2, we move to another side, you will see on the left hand side, this is just a sum of the dj, and dj belong to a DCC set, so this is all still belong to a DCC set. But on the right hand side, there's a negative sign, so it belongs to an ACC set. So a number belongs to a DCC set and the ACC set at the same time, so it must be a finite set. So we know there's a finite many possibility for this. So that means all these di or dj belong to DCCs, belong to a finite subset. Okay, any questions? Okay. Now, still on surface, but now I want to show another result called ACC for numerical trivial pair on surfaces. So, and this will be used when we do the induction on threefolds. Okay, anyway, let's see what the statement. So now we fix a DCC set, and we could show there's a finite subset only depend on this set, such that for any f delta, this pair, low canonical pair with this is trivial, numerically trivial, then the boundary, the coefficient of the boundary must belong to this finite subset. Okay. And the proof goes in this way. So let's see, let's say sketch. Okay, so first, we need to go to a higher model. I mean, we want to resolve a little bit of some singularities, and so that we may assume. So I want to say we may assume the F has only terminal or reduced singularities. So the important for this is there are only finitely many leaves passing through the singularities. So actually what I want is these properties. Okay, then we want to run the four-weighted minimal model program. So observation is that this is, now we know this this numerical trivial. So this is, the KF is numerical equivalent to negative delta, which is not pseudo-effective. So the outcome for this minimal model program or will be a full fiber space. Okay, so let me write it this way. So what I want to say is either this pk number is 1, or we could have the kf negative extremal ray or extremal, okay, extremal ray. They contracts. Okay, actually it doesn't contract. The delta. Okay, I see. Any component of delta. That's so and then for actually this is what I mentioned, and that's for question. I mean, that's a good question. That's what I say. So actually, there's a good observation that if we impose the pair to be low-canonical, that any component of this boundary must be non-invariant. But for the foliated MMP, we only contract invariant divisors. So for any, so that means any such extremal ray won't contract any component of delta. That's a good thing. We will have more control. So if the pk number is 1, so we could have, well, because kf is not pseudo-effective, that means kf is ample. I mean, negative kf is ample. So we still have the bank and break foliative version. I think still proved by Miyaoka. So bank and break give us X is unirule. So we have again negative. Well, Ks is not pseudo-effective. So again, pk number 1 give you negative Kx is ample. Okay, so now we could consider the slope respect to the slope of for the foliation respect to this Kf. So both are ample, so this is positive. Now we need to use some result by Campana and Pao for the smooth variety, and by O for some variety with small singularities. What can they shows that if we have this slope is positive, then the foliation is so-called algebraic integrable. That means all the leaves are algebraic. So, okay, I don't have too much room. Okay, so F is algebraic integrable. So that means we could have, if you consider the universal family for the leaves, I mean, the space for the leaves. So we could have something like so this B is parameterize all the leaves. So if you consider it give you this vibration, but because we have already assumed this condition, and this condition actually will be preserved after running the minimal model program. So S also has this property, and since each singularity has only finite many leaves passing through it, so this is actually a real morphism. So now we get a contradiction because in this is raw surface, so we have Picard number at least 2, so we get a contradiction. So that means we will always that means we won't end up with something anti-ample. So we will actually have a negative extremal ray, and it will give you a more fiber space, and the target will be a truly curve. Okay, let's be right here. Okay, yeah. So that means we actually have this structure. So now from the list 480 mil model program, if this F is journal fiber, so actually we have this is actually equal to 2. This is from the result of 480 and minimal model program. Okay, so or by some indexes theory. And this is because we know the numerical equivalence. I mean, negative KF is just delta this is a delta intercept with F. And now you see something the same as before. We could write this as a BJ and dot F. So all these are some positive integers. So some linear combination of a BJ, it will be a fixed number. So by the similar arguments, we could say that we could conclude that this BJ will belong to a finite subset. So that's roughly the idea how we show these results. So maybe okay, let's stop here. Thank you.
Well, thank you very much. Do you have any question for Ying'an? So in the classical MMP, I think so ACC conjecture is related to the termination conjecture of flips. So in the Fourier setting, can you comment something about in this direction?
Well, that's a good question, and I didn't. I mean, I expected, but I think that's so far not too much evidence for the Fourier setting. Well, that's maybe all what I could say.
You mean no evidence for determination or no evidence for the connection
I
between?
think connection.
Oh,
Maybe well, I didn't check very carefully for the how the classical proof, but I think, well, I'm not quite sure, but I think it's I expect there's some connection. Yeah.
mm-hmm. And also about the foliated MMP. So if the foliation is algebraically integrable, is the foliated MMP reduced to the relative MMP?
Well, almost true. I think I think let me think. I think there's some. I think if you just run the, yes. Yeah, I think after some, maybe be careful for this vibration will be rational. If you just resolve it, maybe, yeah, I think it's almost the relative, it's almost a relative classical minimum model program.
Mm-hmm. Thank you very much. And are there more questions? So if there's no question, then let's thank Yanan again for his nice talk.
Thank you.
And we will resume at 15. So depending on your time zone, so in so either 3:15 or 4:15 or 5:15. Yeah. So see you later.